matrix element will gonna look like this, a running matrix element, depending on the energy of the intermediate 1 plus state here. You can see is consistent with the experimental result. In fact, the first calculation within the shell model, in fact, was predicting the result which came, experimental result which came a few years later. So everything can be done if you are careful. Again, one of the few things was already mentioned, that Ikeda sum rules have to be careful with that. You don't necessarily have to satisfy it, but in this case it's completely satisfied because all spin orbit partners are included. Another thing which is typical to shell model is that this combination of GA times sigma tau operators need to be quenched, and I'll talk a little bit more about that. For PF, the quenching factor is pretty stable at 0.74, was checked out in many charge exchange reaction and looks pretty stable. So therefore, a little bit more about how we do the shell model for those of you which are not completely familiar. So in general, of course, we have a valence space which does not include a core. The core is taken separately. We have a G matrix pretty much like as a starting point as QRPA, but after there is some core polarization down here, because otherwise the pairing doesn't come right. And even then, if you try to do any calculation, you get anecdotal kind of confirmation, but in general doesn't look good. So what people are doing, starting in the 80s, they are doing some fine-tuning, trying to maintain the information from the G matrix plus core polarization, and try to fit or fine-tune the excitation energy for a large number of nuclei and states. The trouble with that is this fine-tuning does not include observable, they only include energies, and when you try to look to observable, what happens is they look more or less okay. For instance, the gamma stellar looks pretty much correlated between theory and experiment, but it's not one-to-one, so you have to multiply by this quenching factor. For SD is a little different, it's 0.77. Now some people have second thoughts about that. They believe that the quenching factor is not a quenching factor coming from nuclear structure, but they believe the quenching factor is a quenching factor of the axial current here, and there are ways of justifying this using two-body currents, three-body interactions, and so on and so forth. So, of course, this is not yet settled. In fact, we know from all our calculations the nuclear structure plays a significant role, and justifiable so, because what we do in this valence space, we actually normalize the wave function to 1, while the many-body wave function will be normalized to 1 if we include all the orbits, and some of this part of the norm is left aside. So this will be a simple justification of why we need this correlation factor, this quenching factor here. We believe that what is needed to be quenched is the nuclear structure calculation with sigma tau operator, not the GA. So that's the way we do this. The calculations of this paper show that at high energy momentum transfer, this GA factor goes up again. So therefore, there's one justification why in all this calculation we don't use any quenching. When we do the neutrinoless double beta decay, we don't actually do any quenching of the matrix elements, but I'll talk a little bit about that possibility in a bit. So we calculate the neutrinoless matrix elements in 3 different ways. We are the only group in the world which can do that, and we get the same results. Let me say from the beginning. So the normal one which you saw in the 2 QRPA presentation of today, the matrix element have 2 pieces. One is a many-body part, which is difficult, and another 2-body piece, which is a little more easier to calculate. And one in which all intermediate states are used in the odd nucleus. In that case, in principle, we can use the energy of those states here. The 2-body matrix element is a little more complicated than usually you can get in reaction theory. There is a 4 factor, which was already mentioned, and in addition to that, there is a short-range correlation, which was also mentioned. There is also finite size effect coming from the axial 4 factor, because the nucleus is large, and interaction is very point-like. This need to be taken into account, and these two things are in general left out when you do nuclear reaction here. So what is observed is that this momentum transfer is about 150 MeV, so therefore the small energy involved in the intermediate states are the order of 10 MeV, so they count very little. So usually people put this a constant energy, and this is called closure approximation. So if you use closure approximation in the shell model and the IBM approach, which you can hear about the next talk, we don't need to more than the initial state and the final state. So in the other approach, if you use the intermediate state, you have to make a sum of the intermediate state, but this is challenging because there are many, even for calcium-48, there are thousands. In this small model space, there are about 100,000. If you want to do germanium, you can see there are 150 million, so there are a lot of states to be taken into account and calculate. Actually, we did that regardless. In particular, for calcium-48, we were able to sum about 1,000 states for each angular momentum. With that, we actually find out that this converging. So in other words, if I'm using this approach or the other approach, I get exactly the same result. This is obviously more complicated, but provide more information. Additional information is that I know the contribution from different intermediate states here. So for example, you can see that the 1+ states in the shell model, at least this is for selenium, in a different model space, so the F7 half is removed and G9 half is added. It turns out that 1+ is pretty large. It's larger than you saw in QRPA this morning. And also 2- is pretty large, but it's not as large as QRPA is getting here. But again, we get contribution. In principle, we can quench all these states if we know how to quench them. We don't quite know how to quench them, but that's how it is. So also I find out that the difference between the closure and non-closure is the fact that we can always use an optimal closure energy. In particular, people use some old table of Tomoda, and for this case, the closure energy is taken to be around 10, 11 MeV. And we can see that, in fact, in this case, the matrix element is much smaller than, much smaller, by about 8% smaller than the one calculated without closure. So we find out one way to actually identify an optimal closure energy which can be used based on our calculation, and it turns out that it depends on the model space and the interaction used, but nothing else. So we can calculate for simpler nuclei and identify what this closure energy is. Okay. So about a year ago, we actually found the third way of calculating the nuclear matrix element. So the third way is based on the fact that even in this estimation, we can rearrange here to find contribution coming from different intermediate state, or find contribution coming from different JF coupling different pair to different J's. Okay, so it turns out that something very interesting pops up, at least in the shell model. So you see there is a big contribution to the J equals 0, to the I equals 0 for the coupling pair to 0, and the 1 to 2. The other one are pretty small, and in fact there is a strong cancellation coming from I equals 0, meaning a strong pairing, and I equal 2, which comes from higher seniority, which we break more thoroughly. I remind you again that in the shell model we don't really have, we have all the symmetry included. We don't have any problems, any symmetry. Particle number is conserved, angular momentum is conserved, parity is conserved, everything is conserved, even center of mass motion is well carefully taken into account. So you can see there's a big cancellation here. This is roughly 8, and this is roughly 3.5. If you subtract this, you get 4.5, and the rest of roughly 0.8 you get from the small pieces. So based on that, about a year and a half ago, we looked to a different route. And the different route was to, instead of going to the intermediate nucleus, is actually to go to calculate the nuclear structure part here by taking from the initial, take a pair of neutron out and go germanium 74. Of course, you can go on the other side as well. So this pretty much is the spirit of the reaction which are planned to be done here, and we saw some talks today. So if we do that, we find out first of all that that these are the light neutrino matrix parameters, the heavy, and somehow they are split. This is a total on the first line. This is only 0 and 2 because these are the most important, and finally it is only 0 on this side. So you can see that this is versus the energy of the intermediate nucleus here of these states. Here. So in all cases we get exactly the same results regardless of how I look at it. But in addition to that, this also obviously came out that it is interesting because, in fact, we can use more experimental information to test the nuclear structure calculation. If you go to the intermediate odd nucleus, that's more difficult. Many nuclear structure theorists are going to tell you that odd nuclei are difficult to describe. Well, these all are even nuclei. So we have very simple contribution only from the 0 and 2 mainly, and this can be tested in pair transfer reaction. Now, I'm not a specialist in reactions, but Alex Brown calculated, just I believe after he published the paper, John Schiffer sent an email to Alex and asked him to look to his old paper from 2007. And he calculated, he dumped all this amplitude here in Fresco, and he calculated the cross-section 0. And he said there is still this factor of 2, which is pretty well known, but in general, it seems that there is better than comparison with simple WBA. So this can be used, the shell model amplitude can be used to calculate some reaction if necessary, and probably comparing different nuclei. This was done only for germanium 76. They can put some extra constraint of nuclear structure. In fact, coming back to the goal of this workshop, this was the first time which people thought that they can nail down the nuclear matrix elements, starting doing a simple or complex nuclear reaction. In fact, about 10 years ago, I was in DNP meeting in Hawaii, and John Schiffer famously stand up and said that this is too an important problem to leave it to the theorists. But Wick Hexton, which was in the room, said, well, how do you plan to calculate to do some low energy physics experiment which can use the same 4 factors which are necessary for the double beta decay. And after that, I believe John came to the conclusion that it's better to help to constrain the nuclear structure rather than extracting a matrix element directly. And he did a lot of work in that direction. I'm going to come back pretty soon. So now, these are the isotopes which are mostly heavily investigated today. In essence, you see there are four of them, and this is what different people promised recently what they can do in the next number of years. In terms of probably the most exotic claim come from Nexo, which is the next iteration of EXO, which they believe they can go something close to 10 to the 28. I believe Hiro said that the solar neutrino are going to spoil that experiment, but then anyway, there is a big drive towards doing a one-scale experiment and more. And you probably know that ANSAC committee approved this, and they are still struggling between the EXO and the Majorana demonstrator. So hopefully at some point they'll decide which one should be funded, maybe both. So anyway, so these are some timelines, but here is I'm going to give you some matrix elements and make some comments about that. This is the line neutrino exchange matrix elements. On the left side are our calculations, the shell model. There is some other older shell model from the Strasbourg-Madrid group, which are the rhombic blue here, and there are some other models, mostly QRPA and IBM2. In particular, you heard today that if you try to approximately take care of the isospin symmetry, which in our case is actually exact in the shell model, there are some adjustment you should make. For the QRPA, you heard from Professor Fessler, is about 10%. It appears that from IBM in some cases actually a little larger. So it's a difference between 2013 and 2015 results here. So we can see that now our results and the IBM results for selenium at least are pretty close one to another. This works well in this region, less on the other side, but that's about it. What the meaning of this bar, you'll see I have bars here which have not real uncertainties, but you'll see what they mean on the next slide. We already heard about different short-range correlations. So these are the heavy neutrino exchange nuclear matrix elements. Then again, here I added the T124 besides the others. So the lower part correspond to the argon V18 Bruckner type short-range correlation, and this one are the same Bruckner but based on CD1. And you can see the difference. The difference now is even more dramatic for the heavy neutrino, because this is a short range. The operator is like a delta function, and therefore the short range is very important. Most of the others, which are another shell model, and the QRP and the IBM pretty much are in the same range. The QRP are a factor of 2 to 3 larger for this case, and this needs to be settled up somehow. And okay, you don't see very well here because the diagram was moved up. This was made on a Macintosh and with a Windows computer. This is a 2-pi exchange NME, and these are some old results for Tübingen group in green, and our results are the bars, and they are not to be compared because the Miller-Spencer, the old Miller-Spencer was used in the QRPA results. So in fact, you should compare the green with the blues to make a good comparison. All right, so one thing that I already mentioned which affects our calculation is the model space. As I said, the model space is pretty small, and because of that, sometimes people claim that we don't have enough pairing inside that. It seems to be true at least for the heavy neutrino. It turns out that recent comparison we did is that for the light neutrino, the cancellation still remains pretty large, even if we had more orbits in the space. But for heavy neutrino, it appears that the pairing contribution is a little larger. So one way to deal with that is to use an effective operator. In fact, the goal of our community, at least in the United States, is to actually not only derive consistent Hamiltonian starting from ab initio type of interaction, but in addition, we'd like to have also effective operators. So John Engel and his collaborators, he actually had 2 papers on that. So he's doing the effective operator exactly in the same spirit as the core polarization is done for the normal effective interaction. So in this case, instead of having many diagrams with many effective interaction in between, in fact, one is a weak interaction coming from the operator, and all the others are normal strong interaction contribution. And it turns out that in this case, there are some changes if we go this way. In fact, we tested that somehow so that sometimes the contribution, at least for the calcium, is very high. It's about 60–70%. But for the germanium and selenium, it's actually only 25%. So it turns out that the calcium is a little more complicated. And the rationale is, one of the things is in the PF we miss the 2 minuses. So all the negative states are missing. And we checked out by adding the ASD to the PF model space. There are a few interactions which are not really well tuned for multi-particle, multi-hole. They are mostly 0 h bar omega good for 0 h bar omega calculation. That'll be good. But we use those 2 interactions. One is from the Strasbourg group, and the other one is coming from Japan. And we do 0 plus 2 h bar omega calculation, and you can see in some cases also get 60% increase when they include the SD, because in that case the 2 minuses are coming in. So in a sense, these 2 are consistent when you use an effective operator, at least for calcium. And the explanation is